So we move on to our two flash presentations next. So the first one is going to be given by Patrycja Bartkowiak from Strathclyde, and it's about accelerating drug release of FDM 3D printed tablets through model-based structure optimization.
Thank you. Right, hello everyone. My name is Patrycja and I will briefly take you through my project, but I will start with the question. We all know there are many medicines with fixed strains with, say, great therapeutic index on all of us because one size fits all, right? No. No, we are all individuals and the therapy should be selected considering our BMI, our lifestyle, our health and other factors. But what if I will tell you that we are able to develop the tablet that enable customized drug load, control over release profile, and also thanks to the 3D printing, well, through the pandemic and shortages, they would love us for this, is actually manufacturing tablet on demand while being beneficial for the industry as well because it reduces the costs and wastage of the material. There's less considerations about the storage conditions that we require, but also the floor space because, well, 3D printer is quite compact. So how we design the tablet, first of all, we have our specification, which is the drug weight, so the drug loading, and the dissolution of interest. Then from the weight and the known density of the material, we can calculate the volume and define the surface area. And next we are building the model of the tablet based on the mathematical equation, where we are implementing the model parameters, visible on the picture, and the volume calculated. Then we are optimizing that structure, and what it does actually calculate again volume and surface area matching our specifications. Next, we are ready for 3D printing, so we've got our material which we feed through the gears, and then it's passed through the nozzle, which is under set temperature, and extrude the material onto the platform according to the coordinates in our G-code. And our final stage is the physical chemical characterization. So we want to see how well the weight of the printed tablet and the diameter matches our designed ones. And we want to see actually if we are achieving the dissolution of interest. So this is one of the results. As you see, we have a solid tablet, and my infill proved that we can accelerate the dissolution profile. But if you like to know more about results, drop any ideas, ask me questions, or clarify one size doesn't fit all, then please just pop into poster number 30. Thank you.
Our second flash presentation is from Suruthi Gnanenthiran from Sheffield. And the title is A Mechanistic Approach to Understanding the Relationship Between Agitation and Agglomeration in an Agitated Filter Dryer.
That's Chris. So hi everyone, my name's Suruthi. I'm going to be telling you a bit about my project, which is looking at undesired agglomeration in agitated filter dryers. So you've all probably become very familiar with this diagram by now, but it shows some of the various steps involved in manufacturing APIs. And I guess what I really want to point out is the isolation stage, and specifically drying. So that's an essential part of virtually all API manufacturing processes, but currently there's a lack of predictive tools when it comes to drying, more specifically agitated drying. So agitated dryers, why do we use them? So by having the agitation and that improved heat and mass transfer, we can get reduced drying times, improved uniformity, and better mixing, all of which are really beneficial. So makes you think, what's the issue? So by having these intense drying conditions with the agitation, you can get either undesired attrition and breakage or undesired agglomeration, which is what my project is focused on. So the consequences of having this undesired agglomeration, firstly, you can get API that's out of specification. So you want to preserve the particle properties achieved during the crystallization. In extreme circumstances, you can even get hard agglomerates that damage your equipment. It requires additional unit operations to delump this, and that results in increased cycle times and cost. So this takes me on to the experimental work that I've been doing. So drying in an agitated filter dryer is quite a dynamic process. We have the agitation, but there's also the heat component, which facilitates these liquid bridges solidifying and forming these agglomerates. And the approach I'm taking is basically decoupling the two to look at the effect of agitation alone on the agglomeration that we see. And I guess what I'm investigating really is the hypothesis that this agglomeration behavior is a function of the agitation inputs. That's both the agitation speed and the agitation time. I'm working in a small lab-scale agitated filter dryer, and you can see a cross-section here. I'd like to mention that the vacuum was provided kindly by Vacuum brand, who are also downstairs with an exhibitor stand, so do check them out. And yeah, so I investigated 3 different agitation speeds, which were designed using scaling indices of pilot plant agitated filter dryers, and 3 different agitation times. So this is just some preliminary results, but it's quite interesting because there's not much literature on undesired agglomeration agitated filter dryers, but some papers suggest that by having higher agitation speeds, you get less agglomeration because it breaks up your agglomerates. But what I saw is actually quite the opposite. So here is a graph of my sieve sizes and my percent passing through each sieve. So the less you have passing through, the more agglomeration you have. And what I'm seeing is as I go from 45 to 65 to 85 RPM, I have less and less passing through. So that's more agglomeration, which I found really interesting. If you'd like to hear my thoughts on why that is and see some of the work I did looking at the effect of agitation time as well, then please come visit me on post number 31. Thank you.